This is 1.3. This is the last part of your 1.1 to 1.3 notes. So we're going to look at continuous functions. A continuous function basically is a graph that has no holes, gaps, or breaks. So think of it like this. As long as you can put a pencil on your graph and go from one end to the other without picking it up, that's continuous. If you have any breaks in there, this is not continuous. Or if you have two pieces, that is not continuous. So it basically needs to put your pen or pencil on one end and go to the other without picking it up. Okay. The continuity test, this is going to be a big part of your calculus. When you take calculus next year or in college, and you have to decide whether a function is continuous or not, these are the things that you need to do, and these are the steps that you need to take to prove it. And on every calculus test, they expect to see all three of these listed and all the three of these checked. I want you to put this on your yellow pages. I will explain the yellow pages in class, because this you need to take with you to college. The yellow pages I will give you as a tool to keep all of your formulas and things like that I think you're going to need in calculus next year or in college. So a function f of x is continuous at x equals c. So at a certain point, if it satisfies the following conditions. Okay, so the first one is that your f of x is defined at c. That means that f of c exists. So you can basically find a point. So if I said to find, if c was, say, for example, 2, if I said to find f of 2, you'd be able to find a y value. So you have to have an actual point there. You can't have any holes in there or any gaps. You have to be able to actually find a particular point. Then step 2 is, we're going to talk about something called limits here in a second. F of x approaches the same value from either side of c. That is that your limit as x approaches c, so this is the beginning of limit notation, of f of x exists. So what that means, oops, I don't need this. What that means is, if I were to, let's say, have a particular point on this graph up here, okay, if I come from the left and I come from the right, I'm going to end up at the same point. Whereas if you look at this function up here, when I come to the left, my y value down here is going to be very different than my y value up here. So coming from the left and the right, your function has to come to the same y value. You have to have the same y value both ways. And then the last step basically says, in order for it to be continuous, the value, that your f of x approaches from each side of c is f of c. So in other words, you're basically kind of going to combine these two together. So as long as this f of c exists and you can find a limit, you're looking to see that your limit as x approaches c from the left and from the right is the same as the function. So as long as the number that is approaching from the left and the right is the same as that actual coordinate, then your graph is continuous. And these are the three things that you have to do in calculus to prove that a function is continuous. And when you get to calculus, you're actually going to have to state it. So I would kind of keep this on the sideline. We're going to talk some more about these as the year goes by. So let me move this up a little. Okay, so we're going to look at a problem. I want to determine whether 1 over 2x plus 1 is continuous at x equals 1/2 using the continuity test. So the first thing I have to prove is I have to prove that f of 1/2 exists. So I have to plug in 1/2 and then 2, it's going to give me 2. So I have a point of 1/2, comma 1/2. So I know that f of c exists. So f of 1/2 exists. Okay. Then I need to check my limit as x approaches 1/2 of my function. So if you go back to, and we're going to continue on this a little bit more later on when we get to chapter 2. If you remember from algebra 2, in order to graph this function, it's a rational function, I have a vertical asymptote at -1/2. So I'm going to kind of just eyeball it. I'm not going to be exact on this right now. I also will have a horizontal asymptote. Since x is my largest variable, my asymptote is going to be y equals 0. That will be my horizontal asymptote. And your graph is going to, and if I check, I know that I have the point 1/2, 1/2. So I know that my graph is going to be up here. Oops. Down here. You just need a rough estimate. So if I'm looking at my limit as x approaches 1/2 from the left and from the right, it's approaching that point of 1/2. So I do have a limit from the left and the right. So my limit does exist. So for 3, as long as my f of 1/2 is the same number as my limit as x is to 1/2 of my function. And it was. This was 1/2. And this was 1/2. So as long as they're the same, this is continuous at x equals 1/2. Now keep in mind, they said at 1/2. They didn't say everywhere because we know that it's not going to be continuous at -1/2. If I had changed this problem to x equals -1/2, that would be a very different scenario, because if I plug in -1/2 here, you would have gotten an undefined. So you have to be careful which one they ask you for. Just because the function is not continuous doesn't mean that it's not continuous at a certain point. Okay, next we're going to look at, we kind of just talked about limits a little bit. So the concept of approaching a value with or without reaching it is called a limit. Okay, so my limit, this is the limit notation, limit as x approaches 2. So here's my x value of 2. So basically, as I'm approaching 2 from the left, I'm getting closer to 4. As I'm approaching from the right side of my graph, I'm also approaching 4. So my limit is 4, okay? What you have to be careful of is there's an open circle here. On limits, it does not matter whether that's an open circle or a closed circle, because all a limit is worried about is what is that number approaching from the left, what is that number approaching from the right. It's approaching 4, okay? It's kind of like less than or equal to, or less than or greater than. It's up to but not including that point. So a function value is very different than a limit value. So here, your function at 2 is 1, but my limit as x approaches 2 is 4. So you have to be careful that these are not necessarily going to be the same. So for the limit, you're looking at what the y value is as your x value is approaching. For a limit, you do not necessarily care about what the actual value is. So this point here is not going to matter at all when you graph it. Oops. Green, come on. That's not going to matter at all. Okay. Next, we're going to look at types of discontinuity. So let me move this up. And there should be, and I don't know why it doesn't come out on here, there should be a 3 on here that says discontinuous functions. Okay, so there's 3 types that we're going to look at. I'm going to draw a graph for each, and then we're going to look at the verbal description. So an infinite discontinuity means at some x value, I have an asymptote, and on one side, it's either going to positive infinity or negative infinity, and the other side, as it approaches that number, it's going towards the other one, a positive infinity or negative infinity. So up here, it's going towards positive infinity. Down here, it's going towards negative. So at x equals c, your graph is approaching positive infinity, which is this one, or a negative infinity, that's an infinity symbol, which is this one. And that is an infinite discontinuity. There's different kinds, so you want to make sure that you know the names of them. A jump discontinuity basically means what it is. You're jumping from one point to the other. And so if I'm at C, okay, I could have my graph look like, this. There basically is a jump between the two. Okay, so there is a break between the y values at x equals c. So you have two different y values. Okay, and then a removable discontinuity. Let me move this up. Basically means it looks like you have one continuous graph, but you have a hole in there. It could be any kind of function. It could be that. It could be a line. So at C, okay, so you basically have a continuous graph except for a hole in your graph. So basically they've removed a coordinate. They've removed a y value. So basically it looks like it was continuous, but it's not. Your infinite and your jump discontinuities are also called non-removable discontinuities. So if you hear that referred to them, that is what they are referring to. Okay, I think that's it for this slide. Let's go to the next one.